The panel discussion, and unfortunately we have lost some of our audience, being Friday afternoon and all. But I think after hearing everything that has been going on, what I would suggest is to think a little bit about, as a society and in general, in terms of thinking where the technology is going and where things are and where are the needs of the people in the next several years. How do you perceive the area of computational intelligence to be, and what are some of the key challenges? What we want to do in terms of research? A lot of times, especially in universities, if you can convince people to fund your work, you can pretty much take your research anywhere. Of course, in order to fund your work, you have to put together a proposal that can convince people that what the society needs and what the economy may need is in line with what you're suggesting. So there are certain trends in technology, and we heard from our speakers today. And what I would like to do in this discussion is to ask our distinguished lecturers, distinguished guests, to talk a little bit about for a few minutes, 2, 3, 4 minutes. What they think are the key grand challenges in this area, and think a little bit outside of the box of what you think may change, not only in the next 1 or 2 or 3 years, but a little bit longer term, and see if there's if there is some consensus about what we consider or whether we think in different directions. Of course, nobody knows the future. That's given, but it's important to since we have this experience, researchers, to ask this question. So the panelists are in alphabetical order. So I'm going to ask Piero Bonisone, who also has the technical. He has a long technical expertise, but also the experience of working in industry for many years. So he has a very good intuition, and he gave some of that intuition today in his presentation. But so this is a continuation of what. If
I can borrow that, so people can read also some of what on my cheat sheet.
Oh, okay.
Just
yeah.
This is a freshly minted slide. I did it while I was falling asleep a little bit. But it was just trying to capture some, look at me, but then you can look at the slide. This morning I told you about people, the cloud, and analytics, which is a combination of computational intelligence techniques. So let's take the crowd for granted, is already here. How do people it says, how do people react? What are the people's needs? I'll say people are part of a solution. And a properly motivated crowd that is willing to participate. And remember, a crowd doesn't have to be just an external crowd. A company with a large number of employees has an internal crowd. Right? So it's a way of distributing tasks in a way where you're creating a small market. And part of the problem is, okay, if you want user-driven, I have user-driven search. One example is active learning. In machine learning, active learning has to do with asking a very small number of questions to a user, and those questions the answers is guiding the search in the problem space, and this guy is determining the next question that will be the most discriminant given what you've got so far. So again, it's not a crowd, it's one person, but it's helping you searching. We talked this morning about many many criteria optimization, right? And I remember Peter Fleming in the first symposium on MCDM, where he was talking about in design problems when you have 10 or 12 criteria, most of the techniques fail, right? That do the entire search. But if you look at a partial run of your multi-objective evolutionary algorithm, and you, for instance, you're using parallel coordinates, a thread through a coordinates is a solution, right? You can start seeing, for instance, that certain threads are parallel, do not cross. That means that those two objectives are consistent, they're not competing. You're reducing the dimensionality. If you see that all of a sudden the threads are going through a very narrow interval, you can say, well, I'm going to take this as a constraint now, just to be satisfied, and remove it as an objective. And so you're, again, quickly providing a feedback while you're searching for the solution, and you're guiding that solution search. So that's what I meant by user-driven search. I don't think we're doing much of this. Most of our algorithms tend to be running in batch mode. Okay, so again, the user or the crowd as a resource is the mantra. The next one is integration of human and computer agents. When you have both of them, how do you know who's right? So I'm saying QA is quality assurance, right, of the agent's outputs. For instance, if there is a bias in the crowd, I want to use some machine learning techniques to recognize the bias and correct it. If there are inconsistencies, I want to make changes in whatever is the majority of it. Again, it's an area that we have not done much research at all. I said, what is the role of a crowd? It can be data collection, local computation, model creation, as in the case of Kaggle.com, model output interpretation. Someone else models is interpreted. Now, in this case, it would be a crowd of experts who basically say, well, this is what analytics tell you. The answer is 42, because that's the universal answer you all know. But I know how to tweak it to make it 41 or 43, depending on some trade-offs. Again, it's finishing the solution. And we talked about what are the incentives for the crowd, you know, beside money, glory, and fame, or credential, or creds. And how do you certify that the people who are doing that solution have the right skill set? And finally, collaboration tools to augment the collective intelligence. And I'll be very quickly on the algorithm side, I put scalability, scale, scale, and scale. That's the biggest challenge, is scaling the volume of the data we're handling with. We're handling both dimensionality of the feature space as well as number of records. It's scale in the number of models that we want to handle. It's scale with the resources that we want to apply to this. And so this requires some distributivity of our algorithm over a cloud or a cluster of nodes. Anytime algorithm, which is a trade-off between the resource that you're going to apply and the output quality you're going to get. So there is some work at Berkeley again on this, but it's just scratching the surface, to say if for different algorithms, I want to tell you how much time you have to wait to achieve this confidence intervals given this number of nodes, or vice versa, if you stop it at this time, what should be the expected confidence of interval around the solution? Fusion of ensembles, of course, is what I like, so that's my bias, but should be agnostic. If it's customized, if it's tailored, it doesn't scale up. And agnostic means touch-free. It may not be as high quality as something which is customized, but you can increase it by the magnitude, and you're not the bottleneck. Anytime that a human is in the loop, unfortunately, we're the bottleneck, right? Everything which has to do with high-performance computing, storage, computation, power, bandwidth, is going to increase somewhere between a factor of 3 or a factor of 4 by 2018. Human cognition and abilities will stay constant, right? So again, recognizing that we're the bottleneck, we don't want to be at that lower loop. We want to be at a much higher loop, an outer loop, not an inner loop. And finally, and this is actually refreshing, there is some very fresh results, is how do you do sampling in very large data sets? Because subsampling induces biases. And there is something called the bag of little bootstrapping that was developed very recently by Michael Jordan and Asriel, I forgot his last name, at Berkeley, that basically allows you to do bootstrapping or bagging, which is sampling with replacement, at the petabyte level. Now, why is this important? Because when you're doing sampling with replacement and you have n records, you end up with 63% unique records. That means that, okay, you're smart, you don't store the records you're not sampling, you only store the record that you've sampled, and you put a weight, which is how many times did I sample this? And the sum of the weights add up to n, right? So you save 27% of storage. So if you start with petabyte data, you still have 630 gigabytes of training set for every model that you want to do. And you want to do, say, 100 times, you cannot do it, right? So what they did, they said, well, instead of doing that, let's have, it's a different trick, where I use a much smaller number, like 4 megabytes of data, of unique records instead of 630. But I sample it as long as the original data size, n. So I'm having a very tedious long sampling, a very small number of records. The weights will still add up to n, right? And this is like an inner loop. I do this 100 times. I can distribute it over 100 processors very easily, right? Take the average, and that is equivalent to one real bootstrapping at the outer loop. And so all of a sudden, you can do incredible sampling without introducing bias for petabyte data. And this is just one example of a type of algorithms and the type of achievements that we need to get to be able to scale up. So to summarize, it's scale, scale, and scale, and people. Thank you.
Thank you, Piero. Pablo, you already mentioned some of what you consider are the grand challenges in computational intelligence. So what I'm going to do is I'm going to ask you something. So a lot of people talk about big data, and there's something that is the data that we receive and the data that we analyze is increasing by leaps and bounds every day. And definitely you gave an example in astrology where this is definitely the case. And there's a lot of other in traffic, in critical infrastructure systems and so on. But one of the areas that I think may be something that is coming up is in terms of business and industry. Businesses, in order to succeed, need to analyze. They have so much data out there, and they need to analyze that data in order to make decisions where they want to go. And it seems like in the area of computational intelligence, we have not tried to address some of these issues. I don't know if you agree, and whether you think this is an area that is going to become very important in the future.
Yes, of course. I think big data is a very hot topic today. It's declared by the National Science Foundation one of the main topics for research. The thing is like this: the hardware is becoming very cheap, cheaper and cheaper, and then that means that we can put a computer in everything. In your shoes, or on the walls, or in the retail industry, wherever you can put sensors and chips. And that means that we will have tons of data for everything. Of course, financial data, or retail industry, or marketing, or whatever. So we have the technology today to have all the data what you want. So what is the bottleneck? The bottleneck is basically the software, the algorithms, because the algorithms are produced by human beings. So we have this serial work, and then we can, unless we do something like crowdsourcing, we are, the bottleneck is our algorithm. So the main challenge is how to make sense out of this data. That's the main challenge, to find the patterns, to use intelligent algorithms to find these patterns in every kind of big data. For me, it's astronomy. For you, could be retail or industry or whatever. And then biology, of course, is important with the genome. You know, you can have a simulation of the whole brain, or you can have a detail of the genome of human genes, but nobody understands what is doing the brain or the genome. So that's the challenge, to make sense of this large, very big data. And today the problem is that our algorithms are rather inefficient for this kind of scale. So as Piero mentioned it, scale is something that is a challenge, and we have to deal with that. If we are able to deal with a very large scale big data, then the next comes more easily. I mean the reverse of engineering of the brain and so on. We know the scale. If you want to know the scale of the brain, just estimate the number of neurons. So we know the scale. So, but are we able today to deal with this kind of data? No, I think we're not. So this is the challenge for the next 10 years or 20 years.
Mario, if I may quickly jump in.
Yes, that's fine.
Just one other type of the data that was not being well discussed or talk much about it are those related to weather data. I was luckily getting involved with a very large national centers in looking into this problem, try to see how the CI will be able to use that. We're talking about those life-threatening situations when there was a harsh weather comes, tornado, hurricanes. Those are the things that it's just right there. And right now the technology provides a lot of data, a way to collecting the weather data from the human observation to Doppler radars to satellites, image map, and many of them. And the question is, right now, it's, the community is still unable to make the good use of those data. A lot of models that was built only allowed you to look into 3 miles radius, that big space. And so it's virtually useless because a lot of detailed information, you have to look much deeper into that. And those are wonderful data problem presented for this community to really look into. Yeah, and I'm really surprised because when I talk to those people, they know the GA, they know the neural networks, they know the technology available, but still they are not at a hint at a way that they will be able to make the best use of it. And I think that probably depends upon the degrees of the competence in terms of the technology, and it's probably where we could play a major role.
Thank you, Gary. So if anybody feels they want to jump in at one time, that's fine. Otherwise, I'll just proceed with the next person that I can put on the spot, Hisao. So, oh, you have something prepared. I was going to put you on the spot.
Japanese. There's no other way.
You want to stand here?
Yeah. Yes, I think that the challenge is always a clear demonstration of the usefulness. As I think that everyone mentioned this one. For example, I found last week I attended a PPSN conference in Italy, and I found the simulation of cancer growth. Simulation of cancer growth is a simulation, but from this simulation, they can find which element is very important for cancer and which element is not so important for cancer. So without actually evaluating, examining the patient, they say that they can evaluate the effect of the factor or effect of the drugs. However, everyone, I think that everyone talk about this kind of application. So I try to make my presentation more funny. Yes. First question is, do you know when I'm very happy with my student? This question is almost the same as, do you know when I'm very happy with my kids? My answer is, it is when they are highly motivated. I feel very happy when I work with highly motivated students, even when they are not so smart. However, I'm not happy when I work with these students with no motivation, even when they are very smart. This from those discussions, I think that I would be very happy if my computer showed its motivation or intention to work with me. The image is something like this. So the challenge in learning and evolution is to highly motivate intelligent system or give a high motivation to intelligent system. The image of my image of learning of evolution is from that guy and this guy. What? From that guy and this guy. So the challenge is to motivate artificial intelligence systems. That's all.
Thank you, Hisao. Freddy, you talked about smart cities, and we know that IBM is investing a lot of effort into smart cities. And and clearly there's a lot of room for improvement, and I guess that's why IBM is involved in that. And definitely it's true that urban areas are becoming larger and larger. One of the key questions as we move forward, there is a lot to be done to make the cities smarter and have a nicer environment to live in. But one of the key questions is, how do we progress? I mean, who is going to pay for these new developments, and who is going to buy these products in order to make it feasible? I mean, do you have some
so is your question, what is the business plan of IBM? Kind of.
Or you can say what you think are your grand challenges.
Yeah. So at Cool, I mean, a lot of people came to us and say, okay, you do smart things, and then you get the data, and you do smart things. You give it for free, and where do you get the money from? You are a company, so what's the deal? And actually, the main thing is we show that IBM is a good data integrator and is doing really nice research. And if we are in an environment where we can have access to the data, and then if we have access to some experts, then we can do smart applications. We can really help the cities, and then we can show very smart application at the end. And then if we show something for citizens, to public government, to public bodies, to government, we show them things, and then at the end, I mean, automatically, if you do things for free and then you expose to public bodies, they will have an impact, and then companies will see that we do things with big data, with very complex problems. And I can cite the big companies, but big companies already came to IBM and say, hey, I saw that what you have done with Stockholm, with Dublin, with this city, we have this huge problem, we have this big data, we don't understand where is the challenge, could you help us? And that's kind of a way to say, hey guys, IBM is investing a lot of effort in doing research, in building software. We have those already. Now it's just up to companies to say, hey guys, we want to buy those one, we want those one. And I mean, and that's fair at the end, because we provide software, we provide products to for instance, to Dublin City, everything we're doing, we're giving for free, and then they use for monitoring the cities and so on. And but that's because they give us data for free. I mean, that's fair. And so that's kind of the. I don't give you the business plan, but that's kind of that's kind of the way we work with different and with different bodies, and definitely then we have. We start collaboration with big companies in Europe, in the world.
That's very good. Jenny, I think one of the areas that people are talking about is human-computer interaction. And it seems like there is a lot of future in that. There's definitely, I mean, we're definitely just at the very basic level. But, you know, people talk about, I mean, we have memory for computers, and then we have memory for people, and then how can we get the two together to communicate and make sense? And of course, we have processing power for computers, processing power for people, and how do we get, and so it seems like this human-computer interaction, and I'm asking you because you gave the presentation that was closer to neuroscience, whether you think this is an area that has a future, and then there's going to be some kind of a revolution in the next 10 or so years. I don't know if you have thought about that.
A good question. I think this is really a good direction, for sure. This is a good direction, and it has tangible outcomes in the years down the road, because these are things which has been, especially multi-prosthesis, these are things where you basically control your external limb, for example, by using your mind. And this has been demonstrated on monkeys and on real humans. The most recent demonstration is people who are implanted with electrodes were able to grab a cup and feed herself. That was the most recent. So this is definitely down the road. It is possible. And one issue is, just now at the during the break we were talking about, it's the invasiveness of this approach, because what I'm doing is single unit probing. This is most effective in animals because we can use animal model. We can probe to the most fundamental computing unit, which is a single neuron. That gives us very high resolution, both spatial and temporal, so we can understand the brain. But for human, unless you're totally paralyzed from neck down, locked in patients, then you can implant. They're willing to cooperate to do anything. But generally speaking, this is not only a handful of people in the world you can do this type of single unit implant. But now there is another implant I didn't get a chance to mention here. That is called the ECOG implant. The ECOG implant basically is a deeper level EEG, deeper level of scalp EEG, where you open the skull, you'll break the bones, and right under the bone, of course underneath the fascia, it's the fat stuff, and you remove, it's called dura. Dura is like a plastic foil holding your brain together, so the smushy stuff don't get lost all over the place. So that is, you peel it, and then you place the electrodes. The electrodes is a sheet. You place it on top of the brain surface. And that has been demonstrated quite useful. And right now, this requires a lot of technological advances. Technological, as I said, in my laboratory, this is basically, I'm learning to do all these sorts of things, handle animals and doing implants and doing the recording. And on the other hand, this is what my friends told me when I started my lab. And basically, every surgeon, neurosurgeon or a heart surgeon or in the laboratory, in neuroscience labs, every surgeon actually is or every neuroscientist in the laboratory actually is a new tool developer. They always discover new tools, unique in the world. Because of the problem is so challenging, and you basically, you create things as you go. You are creative in terms of problem solving, in terms of asking the scientific questions, in terms of coming up with solutions, coming up with answers to your scientific. In the meantime, you are creative to come up with new tools, because nobody has done this. These are brandly new. You just have to deal with it. For a long time, as I mentioned, I just keep having the problem dealing with a live animal. They just keep grabbing their head stage, and I just keep falling for half a year. I don't have anything. So these are the technological advances also is very important in this regard. And in terms of instrumentation, that's what I mentioned. On the other hand, in terms of algorithm, it also poses challenges in the control society, actually, control society and computational intelligence, because right now, many of the algorithms are stationary algorithms. They're basically doing pattern recognition. I see this neural activity. I would say I wanted to move 30 degrees in this direction. I see the other pattern of activity. I want to do the other direction. So you look at it, you remember my first slide where I show the spike trains of a snapshot of spike trains from multiple neurons. So basically you look at this train, see this pattern, you correlate with a control, basically, for example. But the thing is, the brain is plastic. It's a good thing. It poses challenges because actually it's been demonstrated. As we come up with strategies, the brain has already adapted. So now it's a challenge. Who is adapting? The rat is adapting, the human is adapting, or the pattern is actually your machine learning algorithm is doing something off. So it's really a challenge to, right now it's heuristic. Right now it's just, let's try. Let's put a parameter, let's tweak it. And it works for a while, and next morning, let's get up, recalibrate, put another set of algorithms, for example. So that's also very challenging. And other prostheses like memory prosthesis, and also our artificial eye, artificial cochlear implant. These are also, artificial cochlea probably is the most successful because it's earlier. And the motor implant probably are more impressive because then people are, well, everyone is impressive. These are fooling with the brain, by the way. So it's people actually can move their limbs, have use of their limbs is very impressive. So this is definitely a technological marvel. It's really a technological marvel. But in the meantime, I think this is many times now people are competing to be the first to do the demo in the world. And there are a handful of labs in the US and some in Europe are basically competing over time. This lab is competing for the monkey is grabbing a banana. Next lab is this lady is feeding herself with a spoon. So it's basically announcement after announcement, everybody is competing. But underneath, the question I think scientifically of great value is how the brain actually is adapting to the outside. While the brain actually learns as it goes. So these are all great challenges and fundamental science. And everybody agrees the fundamental science is there and it's not touched yet. Now it's just play by heuristics. Yeah.
Thanks, Jenny. Johan, did you have something that you wanted to say, or do you want me to ask you a question?
You may start immediately with the questioning.
Okay, so one of the things that we hear about is dealing with this big data and is the interaction between the between the human user and we provide, we can develop algorithms that can handle millions of data and can come up with results, but humans are very reluctant to use it unless they understand a little bit about it. And so these black box approaches don't seem to be exactly what people want. And so how do we balance between coming up with something that is useful, at the same time people would accept it and make it useful? So I think it fits well with what with some of the visualization tools that you're using, but I think a lot of it has to do with how do you visualize and make sense out of the data, not only come up with some result that may not make sense to some people.
Okay, thank you very much for the interesting questions. Let me first say a few things on the big data. So I think it's in the first place also important to make a distinction between large scale at the level, for example, of a single laptop, because there are, for the daily user, there are really also a lot of applications just on the laptop scale. So if you say big, you also have to specify
how big.
Are you going to work with a distributed environment or just on a single processor or multi-core, for example? So for example, with the class of fixed size kernel methods that we developed for the use just on a single laptop, we can already go to millions of data points for general black box models. So this actually also fits within the primal dual picture that I've outlined. So you start with kernel functions in the dual, you subtract approximations to the feature map, and you can start using these for a parametric regression in the primal. And so you can do it within that picture, not only for classification and regression, but also for clustering problems which are really large scale. We have seen for other methods, like for example the SVM, that there has been for classification a lot of maybe thousands of papers just on how you get this applicable to very large data sets. But if you see then whether you can extend those methods to more complicated settings, then often that's not the case. So it's also important, I think, that those methods are flexible and generically applicable to a wide range of problems. If you have, for example, additional prior knowledge and you want to incorporate it in your model, and finally you have to solve some optimization problem, that you're not stuck. Currently that's often the case. So we really need to go there to algorithms that are generically applicable and that scale. So I think for example, the fixed size methods that we developed are a good candidate. But if you are prepared to work in a distributed environment, there is really a lot of research also in distributed optimization. So that's certainly a promising direction for the future. And also in optimization theory, like efficient first order schemes, scalable algorithms, these are also promising candidates. But yeah, as you say, this is all black box models. But as we have seen, there are several things on which you can start working. You have on the one hand the kernels that you can play with. On the other hand, loss functions, regularization terms. So one way to get more interpretation into your models is to introduce sparsity. For example, in feature selection, if you can get a small set of relevant features, or in combination with basis functions which lead you to interpretations, this may also lead to new models and new schemes, in fact. So, but there also the interaction with the end user is of course important. Often we have the tendency to develop very advanced models, and we know that they will have a good predictive performance. But if you go, for example, to a hospital, then the medical doctor wants to get insight into what the model is doing. But it may also be depending on the application. So, for example, the important application of weather forecasting was measured. Do you really care then about the interpretation of the model? And what is really relevant at the end is that you can predict the trajectory of the hurricane, whether you can have an interpretable model or not. So what I would really also like to emphasize, what the main thing remains is in fact high quality in predictive modeling and good generalization. I would say this is the main important thing. And then in the second place, if you can have an additional interpretation for the user, the better. But in many applications, especially a high quality predictive model, or maybe also characterization of the uncertainties. For example, bootstrap procedures have been mentioned. We know, for example, for LSSVMs, you can view this as linear smoothers, and you can also come up with faster algorithms there to characterize the uncertainty on prediction than by using bootstrap techniques. So we have also reported this in the IEEE transactions on neural networks. So also characterizing uncertainties for many types of models is also important, I think, in many applications.
Thank you, Johan. Very good. Jean, so one of the things that we think of computational intelligence is in terms of the application, and we have heard a lot about this today on how do you handle the optimization of data, the decision making and all that. Another direction is the direction of understanding the brain better. And what do you think? I mean, we have made a lot of progress in the last 20 years, and but maybe not as much as we thought we would be making. If we were to go back 20 years ago, if you ask people, they would think that we would make a huge progress by now in understanding how the brain works. What do you think is going to happen in the future? I mean, maybe you don't know, but what do you think anyway?
I think you give the answer already. The answer is we don't know. So one thing I find quite interesting about understanding brain is if you ask different neuroscientists whether they are sitting from psychology or sitting from medical school, they tend to give quite different answer. If you ask different psychologists or different neuroscientists, some of them will emphasize the fundamental level in terms of physiology, looking at a single neuron, build a computational model using a supercomputer for a single neuron. The other camp is also quite interesting. They are slightly more behavioral. They tend to argue if you want to understand the system as complex as a brain, maybe the level of abstraction for the understanding will be critical. So whether to gain an understanding of how brain works should be at the neural level or at another level of abstraction, it seems to be an open question for some of the psychologists and neuroscientists. I was inspired quite a lot by a particular question, whether that's something maybe both computer scientists and engineers can think a little bit more, because we are building models. Maybe we can consider some kind of different levels of model, that might help us in capture some of the principles which will be difficult to capture at the neuron level. In terms of what I discussed about applications, I won't repeat what I said in the morning, but I thought it's very useful to echo what Piero said first in terms of scalability. Even in understanding brain, I think scalability is absolutely essential. We understand one single neuron does not mean we understand a group of neurons. If we understand a group of neurons, doesn't mean we understand a brain. So the scalability is essential, and then the scalability includes both theoretical research and the practical application. The second word I would like to mention is this reliability, or some kind of notion of robustness, especially for computational intelligence society. No matter what tools we develop, a user will have a question. If I produce a result, how do I know I should trust it, or how much I should trust it? Especially we are looking at these tools in a dynamic and uncertain environment. So I think there are both theoretical and practical challenges. The last one is simplicity. If you ask the question why these wonderful technologies have not been used widely in practice, I think simplicity is one of the reasons, according to my personal point of view. Users like this push-button technology. Push the button, something happens. In evolutionary computation, that does not happen. We need to tune parameters. Users will not have time to tune parameters. They have no idea how to tune parameters. I think that's actually the challenge. How can we get to simplicity? I think we need to have understanding of both the problems as well as the tools we are developing. I think the challenge is not to overly focus on the tools and then somehow miss opportunity to understand the problems. So I'll say reliability, I'll say scalability, reliability, and simplicity are the big challenges.
Thanks, Jin. Gary, I think you were one of the people, maybe the only one, that mentioned education in your presentation. So let me ask you something about that. So one of the things that that we want to do is to teach students, both at the undergraduate and at the graduate level, that would that would have the skills to become marketable in industry and in society in the future. So in terms of teaching computational intelligence, what do you consider to be some of the key tools that we should provide for these students to make them be able to be wanted desperately by industry people, especially, I mean, I'm not talking about in universities and stuff, but to have the skills that would go out there and the industry would want to hire them in order to handle some of the key challenges that are coming up?
Well, I think this is probably a better question for Jenny and her community. That's no easy answer for that. I think each one of us, as an educators, universities, all trying to figure that out. But maybe I would come back to these questions. But before that, I was just trying to thinking about another probably non-technical issue. A lot of things has been discussed already. But I like to bring up another issue is about this publicity, the visibility aspect of the CI technology. I thought for over the last 3, maybe even 4 decades of how many people working in this field are pushing that technology come to the point that we have something that we're really proud of. I mean, we're talking about neural fuzzy evolution computations. Each one have their own life, and it continues to be that way. And the society is really growing, and we're doing as good as we could. And I was really surprised because I thought the buzzword that we use here, neural fuzzy evolution computation, could be just something that we can communicate with a bunch of the engineer, maybe some of those more fundamental scientists study the physics, chemistry, doing the data analysis. But I'm surprised that my wife's working in medical centers with some doctors specialized in the autism and ADHD kids. Those kids, they have some learning behaviors problem. And those doctors, medical scientists, they know what we're talking about as a neural networks, to do the model and the evolution computation as well for a lot of data analysis. And really, that's surprised me. So what I'm saying here is over the last probably 3 decades that we have come to the point that our technology has permeated into every aspect of the science, the business, the community out there. And they know. But the question is, I feel like we come to the point maybe that we are losing some of them as well. For example, there was a good reason why we're changing the IEEE transaction, the names of the neural networks to neural network learning systems. And I remember, Shin will probably remember better, when we try to do that, we have to justify the needs, and we find out that people are not talking about neural network that much now. They do the machine learnings, and they will go back to their machine learning community. And there are people working on neuroscience. They probably don't think they belong to neural network community either. So those are the kind of the things really trouble me a bit is where we really situated, and we have enjoy this growing process, come to the point that we really sort of stabilize now, but we begin to see the new threats because people know what you're talking about, and they just treat that as part of the the technology tool. They could learn over the process from the statistics, from the machine learning pattern classification, things that we all learn through the college educations. And so I feel like we have to really seriously thinking about in the futures what we really substance. A lot of question is, are we really responsible to explain what is the brains? Is that really our job? I mean, probably. I don't think that's something we are really thinking about. We are entitled to come any closer to be able to explain that. But certainly, we are trying to inspire by the way how this complexity of the neural, the evolution process, the way how we communicate, exchanging the idea in a very natural language basis. Those are the things that we treasure, but I think we continue has to take that probably to the next level, meaning hey, maybe we should solving some more difficult problem. Like you're talking about the big data problem, those large scale problem. We probably come to closer to be capable of dealing with those, those critical infrastructure systems. I mean, that's really, really exciting. But we have to be really, working so hard to try to open up the new problem to the degrees of the complexity people cannot even come closer. So I thought that is become the issue connected with education is it's going to be something, we all have the neural network courses, probably, more in evolution computation in the graduate school now. But, how do we sustain this community so it will still be there 20 years from now? And when we look back, it will be very interesting to see, what it's going to look like, what people in that community really study. Or if the CIS is still alive yet, So, for the future president.
Thank you, Gary. So I'd like to, we're running late, I know, but if you have some interesting questions to ask the panel, please raise your hand. So. George, you want to talk in the, it's the big button,
Yeah, okay. I just wanted to ask Piero, I understand the scalability, I recognize it's very important, also the distributed systems and doing things on the cloud, etc. You had a bullet, let's see if I can remember, agnostic fusion of data-driven and physics-based models.
Great memory.
I just wanted, I realize it's important for this to be agnostic, etc. You wanted to get the humans out of the inner loop, but how practical that is? Because customized solutions will give you better results. So if you have this agnostic algorithms, I don't think you'll get the efficiency that you get with a customized solution. So,
well, I actually treat Fusion as just another model. So what I want is to have an automation of that model building. But think of we have object level models, which are the problem solvers, where they're constituting, creating the ensemble. And then my Fusion, which is above, right, meta in Greek, is just another model. I want to automate that Fusion the same way as I'm automating the object level models. The reason for that is very simple. I've been talking to Peter Norvig, the VP for Research at Google, right? And he was saying when you're dealing with the scale that Google is dealing with, any algorithm that you're doing has to be the simplest possible algorithm and has to be as generic as possible to scale up, or you will never be able to accomplish that scale. So yeah, we're dealing with a trade-off of peak performance, if I can tailor it to something, versus general applicability. And if we want to tackle those, the magnitude of the scales that I'm talking about, we have to go for general applicability. My personal view.
Other questions from the audience? Christ?
In dealing with real problems, there is this what we call unbalanced data. Usually the problematic cases are very small percentage of. I heard and I read many papers and presentations dealing with this problem, but I haven't found an answer, a real answer to address the problem. Thank you.
Johan, you want to say something?
Well, for example, in our book, this is addressed, the topic of imbalanced data. So there are several ways that you can go. An easy way is just in the objective function when you have, for example, if you work with least squares cost function, instead of having the sum of the squares of the errors, well, that you split it up into two terms where you give a different weight per class. That is one way, a common way to proceed. Another way is to do a bias term correction afterwards, because often the bias term is not well estimated, and then you might also do afterwards a bias term correction. But if, well, your problem is really very much unbalanced, then sometimes you may also treat it as a one-class problem. And so rather as an outlier detection problem. For example, in problems of fraud detection, for example, if you have phone calls, mobile phone calls, let's say you have a million calls, then maybe only a small fraction, maybe at most 100 of these 1 million are fraudulent calls. So there you have a highly unbalanced problem. So what you might also do is model the class where you have the most examples, and then you may also come up with a predictive model to see whether you are in that class or not. Also in some bioinformatics problems, this is often done. Or you may also use these methods of kernel spectral clustering that I was explaining. So we are currently using this in industrial projects for predicting maintenance of machines. And so people want to predict early in advance whether a machine has to go into maintenance or not. So also there you may use an unsupervised learning technique, and then so instead of incorporating the labels, you may first work in an unsupervised way to model the clusters. And you may also introduce the specific labels. So in this kernel spectral clustering, in one of the last IJCNN conferences, we also, for example, reported a method where you can make it semi-supervised. And so you start from this clustering model as the basis model, and if you have some additional labels, a few amount of labels for these two classes, you may also add this information as constraints, and then you get a semi-supervised learning, which is characterized by a linear system that you have to solve. So there are in fact several ways to go there, and so you should not necessarily think in a supervised way. You may think semi-supervised or even completely unsupervised. But yeah, in the end, whatever approach you take, there is always a solution to the problem. So you may always send me an email, so I can always give you some further information on this.
Piero, did you want to say something?
Just a brief commentary on that. For instance, if you're using entropy-based methods, right, and you have a fractional percent of anomalies versus 99 plus normal, your entropy is very close to zero. So if you use an unbalanced tree, for instance, you will not be able to distinguish that from noise. So what people do sometimes is to say, okay, let me create a balanced tree. I'll do the correction later. The key problem is, if I want a balanced tree, so I start from a 50-50% distribution of the two classes, right? How do I get the 50% of normal out of the 99% plus of normal data? And many times people do just random sampling, right? What I found, I can't remember the author, but I found it very interesting, very useful, is to say, let me do unsupervised clustering in my normal data, because unsupervised clustering will tell me which kind of, if it's a process, many different operating conditions, which are equally valid, but they're different, right? So I get then a sense of a cardinality of each cluster of normal data. And when I do the sampling, I sample each cluster proportional to its cardinality, so I'm maintaining whichever distribution of normality I have. And with that, I can construct a balanced tree. And I do that many, many times, and I do a random forest.
Since we're running quite late and the bus is coming to pick up our guests, so what I would like to do is just wrap things up and just to recap on some of the things that we heard about today and also about the panel discussion. It seems like one of the key issues in the next several years is the dealing with the issue of big data, and big data it's a very generic term, but it is being picked up and being required by industry and by funding agencies. It also has a lot to do with cloud computing, which is another area that is becoming very hot. And it's important for researchers in computational intelligence to be aware of all these techniques, of all these applications that are coming up, so that they can start thinking at a different type of scale and so that they are familiar with some of the key challenges that are coming up, so they think in terms of those things. Of course, it's not only dealing with data and applications, it's also the bio side of computational intelligence, understanding how the brain works, and also not from a biological or from a neuroscience perspective necessarily, but also from a neurocomputational, so how do we develop models that mimic some of the behavior that we see in human people. So what I would like to do with this workshop, some of the outcomes of the workshop is to post some of the presentations or all of the presentations, if the guests would allow it, on the IEEE Computational Intelligence Society website, so that people that hadn't had the opportunity to be here today and listen to some of the presentations, to be able to listen to this, especially new graduate students and people that are looking into this area. and also to come up with an article to be published in the IEEE Computational Intelligence magazine, which so the objective is to be able to come up with a list of some of the things that some of our experts think are important key challenges in the future. And also, if some way we can get across some of the ideas to the funding agencies, I think this is something, another direction that we might want to do. That's some of the things that I have in mind, but if you have some other things that you think that some of the outcomes of this workshop would be helpful, please let me know. I would like to take this opportunity to thank everybody for, I know it's Friday and it has been a long day, for staying until the end. I would definitely like to thank the guests who have traveled yesterday, some of them from very far, and they are very tired and jet lagged, but they have stuck around. Well, they didn't have an option actually, but we'll take them out to a nice dinner tonight, so maybe you can sleep on the bus a bit and refresh yourself and take a shower, and then we'll be ready to go for some dinner and a drink. And it's a great pleasure to have you here, and it's a great honor to have you here and to be part of this workshop, and I hope that something comes out of it. So thank you very much.